Vision-guided outdoor flight and obstacle evasion via reinforcement learning. Multicopter drones have seen increased popularity due to their agility and cost-effectiveness. However, their primary drawback is that they require continuous remote control, thereby impeding usage in GNSS and telemetry-denied applications. Therefore, an open area of research is to develop systems capable of autonomous navigation through cluttered environments to a goal point using only onboard systems and sensors. In this paper, we create an end-to-end sensory-motor policy for outdoor adaptive drone navigation. The policy is drone agnostic, receiving state estimates plus depth images and outputs velocity commands which can be followed by most off-the-shelf drone APIs, in this case the SDK of a DJI M300. To train the policy, we use a combination of privileged learning and reinforcement learning, where optimal trajectories provide a supervisory signal to the reward function. We deploy the policy into the real-world, zero-shot onto a drone and obstacle environments never before seen in simulation. We take a modularized approach to constructing our policy, where a pre-trained image encoder acts as a perception head, followed by an LSTM actor network trained in simulation using PPO. Our training pipeline uses Unity for environment rendering and Flightmare for physics modeling dynamics on a 0.7 kilogram drone. We also incorporate domain randomization by applying noise to the depth images and output actions alongside adding system latency and varying flight dynamics. We use a global motion planner to generate optimal trajectories. We then train the policy using these trajectories as a component of the reward function before fine-tuning the policy in a mixed curriculum environment. We deploy the policy onto a DJI M300 drone with a Z2i for VIO plus depth imagery and a Jetson AGX Xavier for compute. In real-world experiments covering over 650 meters of field trials, the policy overcomes sim-to-real gaps such as scenery changes, sensor noise, and crosswinds. Furthermore, the policy generalizes to a drone 10 times the size of the one in sim, thereby supporting that robust policies outputting high-level velocity commands can generalize to a range of drones. We first conducted trials using VIO positioning, demonstrating a 100% success rate of collision-free navigation, albeit with an average real-world measured distance to goal of 2.27 meters. To decouple the inaccuracy of the VIO device from our policy's performance, we conducted trials with GNSS positioning, getting an average distance to goal of 0.81 meters. Here are a few examples. The top left view is the depth image, and the bottom left view is video from the drone's onboard FPV camera. The bottom left HUD overlay also displays the drone's speed and kph. The right shows the trajectory and obstacle positions for the run. As can be seen by the FPV in-depth video, the environment has numerous objects in view, such as a sculpture, pond, trees, light poles, cars, and buildings. This is a recording of a run in the second field environment with the inverted triangle configuration. For all runs, the drone's max speed is set to 3 meters per second. As can be seen, the drone stays close to the maximum speed through the runs. This is a modified environment where one of the obstacles is hidden behind the first. As the drone approaches, the obstacle comes into view and the drone adapts.